Hi, welcome to another Morphologica video. In this video I'm going to show one of the demos from the first demo video, but I'm going to talk through the code that was used to produce that. So the demo I'm going to talk about is this one here. This was a Keller-Siegel reaction diffusion equation. It's got two hex grids in it, two variables, and it's got a graph visual down at the bottom here. The code is, there's about 250 lines of code in the actual numerical simulation. I'm not going to talk about that, and there's about 250 lines of code to sort of instantiate the simulation and to create the graphing. So that's what I'm going to talk about. So let's just minimize that one there. Pop it in the background, and I'm going to use Emacs as my editor, and I'm going to edit this code, which is in examples. So I'm in the Morphologica base directory, it's in examples, erm.track 2009, and the code is erm.cpp. Okay, so here it is. I'm going to make it big. I'm going to make the text big. Really big, make it full screen. Okay, so what we've got here is, let's skip the headers, let's start at main. I'm going to skip over the stuff about the configuration. So this starts off taking a command line argument, which is just the parameters file, so it's a JSON file. I then I create a configuration object, a morph config object, and I get a bunch of parameters out of that. So I'll just skip over that code down here because it's not relevant to the, or not directly relevant to the visualization. So there's the config code there, and then I come up to some code to instantiate the model object here. So here's an it's called rd-erm. That's the Keller-Siegel system, or the erm.track Keller-Siegel system. So the next few lines of code are just setting up all of the parameters of that object, allocating it and initializing it. So now we've got the numerical simulation. We could actually run that now without any graphing, and then save some data out from it. I've got a little section of code here which just creates a log directory, so that just makes sure there's a directory to put data into, and then I save some data out into that log directory. So now we get to the bit that we're interested in. That is setting up the morph visual object. So this creates the environment, PLT for plot. So I pass in a width and a height in pixels, and a title for the visual environment. And then there's a few things here. So I'm going to set the near clipping plane and the far clipping plane. So those determine when objects are actually visualized. I don't think, to be honest, I should probably just figure out what the ideal values for these are and fix them. But that's what those are there. And then FOV is the field of view. You can change what the field of view of your 3D environment is, so that's what that's about. I set a default Z position for my objects. That's always a negative number. In this case I've set it to -10. And that's where the objects appear when they're first rendered. I can then set whether I want those coordinate arrows to show by default. So if I flip back to the simulation now, these are the coordinate arrows down on the left here. They have appeared by default, so they're showing there. If I press C, then that makes them disappear. If I press C, they appear again. So I can just choose whether or not they should show up initially or not. Okay. So back here, I can say whether or not the title should appear in big blocky text in the environment, and I've said I don't want that. If I'd said true, then there'd be something in this environment saying erm.track Keller-Siegel. That could be desirable if you wanted to make a movie from this run. Okay, there is a scene locked parameter or attribute of the visual environment. If I set that to true, then I can't move the scene around or rotate it. That's useful if you're going to make a movie of your system. And then, oh look, I've just set Z default again to a value from the config file. So there you are, that's irrelevant up there. Let's delete that line. And then this set scene trans XY, that's about setting essentially where the camera is. It's not necessary, you can do without that, but it's useful to see that it's there as an option if you want it. Another feature that you don't have to set, but it can be useful, is to set how quickly the scrolling in and out works. So that's just how quickly the camera moves in and out of the scene. Okay, so we've got a visual scene set up. There's a few other features that you can access if you need to know them. The thing to do is to go onto Morphologica's GitHub page, scroll down to the README, keep scrolling down to the bit that is entitled Code Documentation, and there's a link to the code docs. And if I click on that, I should get there with a bit of luck. And then I'm going to go and find the morph visual object. Here it is. And we've got a few things. We've got a few things like background white. I could set a white background for my scene, or background black. You can see a few of these here that I've already talked about. Position the coordinate arrows if you want to. You can add a label. A bit of luck there's in there. Yeah, you can add a label to the environment, so that this is the page that's useful to go to for information about the API of Morph Visual. Okay, so having set up the visual, now I can add some visual models. So what I'm going to do here is, first of all, I'm going to set up a small vector. This is a 3D vector called spatoff, or spatial offset, which I've set to 0, 0, 0. And I'm going to set two morph scale objects, a Z scale and a C scale. So Z scale for the hilliness of the 2D surfaces that I'm going to plot, and the color scale. And then here's the sort of the main part. We create a hex grid visual pointer with a call to new morph hex grid visual. So there's a constructor. I have to pass in some information from the morph visual, so I have to pass in the shader program and the text shader program. And then in this case I'm passing in something from the numerical computation. That's the hex grid from the computation. So that gives the positions of all of the hexes. The spatial offset for where this visual model is going to appear. This is the actual data that I'm going to visualize, or a reference to the data that I'm going to visualize. The Z scale and the C scale, so scaling of that data for both its location in space and its color, and my choice of color map. There's a number of color maps in colormap.h. They're similar to the, or in fact they are copied directly from the Python color maps. So Inferno here is the same as the Inferno in Python, and you've got Plasma as well, but there's also maps like the Jet map and so on. Okay, so having created that hex grid visual, I then going to add a label to it. This one is the N variable, so it's N axon density. Let's go back and have a look in the there. That's the label there at the top of the hex grid visual. And that takes a position there. That's the position of the label, the color, the font that I want to use. Fonts are quite nice in this system because I've provided all of the bitstream Vera fonts, and they are compiled into your program. So they're true type fonts, but your program at runtime doesn't have to find TrueType font files, so you don't have to mess around installing stuff. It does mean you need to have the files when you compile the program, but you don't have to have the files when you run the program, which is really, really nice. And then those last two parameters are the font size. 0.12f is the font size, and 64 is the sort of the pixel intensity, or the pixel resolution rather, of the texture that will be used. You have to make that not too big and not too small, depending on how big your text is going to be. So you might think, oh, well, I'll just make them all really high res and then they'll look great, but they don't look great. So for the size of the text, as it's going to appear on the screen, you have to have a suitable value in that, and it takes a little bit of trial and error. That's another area where I could improve this. I could probably figure out how big the text is going to be, and guess that to be something that will be acceptable, but I haven't done that yet. Okay, so having added the label to my Hex Grid Visual, I simply add it to the visual model, to the PLT object, and that's done, and it returns an index to that visual. So I can ask the morph visual object to give me the visual model with the index n_idx. Okay, and then the second thing is to set up another 3D map. So that's basically just a copy. It's very similar to the previous few lines, only in this case it's for the C variable, the chemoattractant. The only thing I really change here is I change the spatial offset so that it appears in a different location. I give it it has different data, the C data, but other than that the code's the same. Okay, and then the next section of code sets up a 2D graph with the morph graph visual code. Now graph visuals are reasonably, it's got quite a lot of options, so again go to the code documentation and let's find it. Graph visual, there it is. There's lots of information in there from the code documentation, but here's how we actually create one. We do the same thing. We create a graph pointer of a new graph visual, and we pass in the visuals shader program and its text shader program, and then a spatial offset for where the 2D graph is going to land. So there's the offset there. It's across a bit, 0.5, and down a bit, -2. And then I say to that graph that we're putting this graph on a dark background, so it will automatically then make the axes and the text white. And I'm going to say that this graph should be two-dimensional only, so it shouldn't rotate when the environment rotates. So if I go here, zoom out, rotate the environment, the 3D graphs all rotate round, but the 2D graph doesn't. I'm going to tell the graph what the limits are going to be on the X and Y axes. So there's the X axis limits, and here are the Y-axis limits, and in fact I'm getting the Y-axis maximum from the config file with a default of 40,000. Okay, and I have to set some of these things because I haven't actually given any data to the graph yet, because there is no data for the graph because the simulation hasn't run yet. I say that the policy for this graph is that it's a style policy of lines, so it's a line graph rather than a line and dot graph. There are various other options for that. You'll find them in the documentation. And then I'm going to make, let's see, looks to me like YY isn't used there. No, that's unused. Okay, so then I set the X label for the graph, Y label and X label for the graph, and then I call this function called prep data, and what that does is it says, okay, there are going to be data points called with a label n and there's also going to be data points with a label C, and I haven't got any data to put in there, but that tells the graph that they're essentially going to be two lines on this line graph. And then I call this finalize function, which sets up the graph ready. It basically draws all the OpenGL objects for the axes and the text and so on. And having done that, I then add that visual model to my morph visual plot object. Okay, there we are. So then there's some stuff to do with running the simulation. I run simulation, call the step for the simulation, and then I've got a little if here. So every few steps, so if plot every, say, is 100, then every 100 time steps in the simulation, I'm going to update the graphs. So these are the functions for updating the data on the graphs. The first two here are for updating the hex grid maps. So this one, this first bit here is obtaining the pointer to the model based on this index n idx, casting it to a visual data model pointer. That's a sort of shorthand for a visual data model pointer. So that just gets the pointer to the visual data model. Visual data model is a kind of intermediate class which handles the data in the hex grid. And from the visual data model class, the update data method is called. You pass in the current value of the n variable. That's not one hex, it's not 0 for the first hex, it's 0 for the first collection of hexes. This model is set up so that there could potentially be more than one n in each model, but in this case there's only one n, so it's n0. And then the same line for the C variable, and that puts it in the C IDX model. Okay, so that updates the two hex grids, and then I append data, the sums to this. I append to the graphs the sums for n and c. So graph 1 append, and I append the x value, which is just the time. So that's step count times the time step, and then the sum of n there, and this last one is the index, so that's the line index, so that's essentially the 0th line, and then I append to the first line the sum of c. So simple as that to update the data, and that's basically it for the visualization. It's not basically it, because I have to handle the rendering. So when you've got an OpenGL environment, you have to call the morph visual render function. Now I could call this on every single time that I update the plot, but that might be a little bit slow, so I might want to do it faster than that. But I don't want to do it any faster than 60 Hertz, which is the refresh rate of my monitor. So I basically test. I put a timer in since the last time I rendered, and once that timer goes above 17 milliseconds, then I will call the render function, and that gives me a nice smooth bit of graphics. So this is just handling a kind of set of timers, or a timer called last render, which allows me to render it smoothly. And that really is it for the visual code. So I will end the video there, and I hope you found it useful.